2x squared, 1 minus x squared, 1 minus x squared, y double prime, plus 2xy prime equals 0. Okay. Let me see again. 1 minus x squared y double prime, 1 minus x squared y double prime, plus 2xy prime is equal to 0. Okay. Second order linear equation. Okay. We know we want to apply this. Oh, I have to give you a homogeneous solution. Y1 equals 1. 1 is a solution. That one's easy, right? Because there's no y, it's just derivatives. So what's the simplest solution? Y1 of x. See, here's an example where if you looked at the equation, okay, you could almost, wait a minute, there's no y in there, just set y equal to a constant. What's the simplest constant? 1. Okay? That's a solution to the equation. So just knowing that, we can now get the complete solution. Because we just need one more independent solution. 1 is fine, okay? As long as the second solution is linearly independent, right? We can't have a solution say y1 of x equals 1, y2 of x equals 10. Those are functionally dependent. I mean, they're linearly dependent, right? One's a multiple of the other. But any function of x that we get is going to be independent of that guy, so we'll have all the solutions. Okay, we're going to apply that formula. Again, don't forget, put it in the standard form. So we have the second derivative of y with respect to x plus 2x over 1 minus x squared dy dx is equal to 0. Okay. Actually, I'm going to make it, so I want you to log in. You don't have to do this, but this will just make it a little easier. I can get a minus in there. Let me do that as minus 2x over x squared minus 1 times dy dx is equal to 0. Okay, now it's our standard form. Second with respect to x, p of x dy dx. Okay, there's your p of x. Okay, be very careful over here. Okay, this is the p of x. It includes the minus sign. Some people make that mistake, right? What is p of x in words? You put the equation in the standard form, and you pick out the coefficient of dy dx. The coefficient dy dx is minus 2x over x squared minus 1. Okay? It includes the minus sign. Okay? So, minus the integral of p of x dx, because that's what I'll need, right, is equal to integral. See, now I do minus p of x, I get 2x over x squared minus 1 dx. Okay? And this one is simple to integrate. It's just a log of x squared minus 1. Right? But differentiate using the chain rule. 1 of x squared minus 1 times 2x. It's exactly what I have. So now I need the exponential, right, of negative the integral of p of x dx. Well, what's the exponential of the log of x squared minus 1? It's x squared minus 1, just by definition of log. Okay. So now, let's see what our second solution is. Our second solution, we'll call it y sub 2 of x, is equal to, you take your first solution. What was our first solution? It's 1. Okay, we don't have to write that in. So you have 1 times, then we have the integral. 1 over y1 squared here is very simple. It's 1 over 1, which is 1. And then you just have left exponential of minus the integral of p dx, which is x squared minus 1. Don't forget the entire x squared minus 1 dx. Okay? And that, if I do that integral, now here I have to be careful, it's x cubed over 3 minus x. Right? Now, you cannot say it's x cubed minus x, right? This is a homogeneous solution. Any multiple of that is a solution. So you could set y2 of x to be x cubed over 3 minus x, or you could say y2 of x is equal to x cubed minus 3x, because one's a multiple of the other, okay? So that's our second homogeneous solution. And just remember, you can't throw away the 3 over here. If it was just an x cubed over 3, yeah, then, yeah, scale it by 3. But notice when I do the integration, I'll do the integration, exactly. And then I can get rid of constants that I want by just scaling this somehow. So leave it like this, or you can say it's x cubed minus 3x. So I'll put down here, or y2 is just x cubed minus 3x. Let me just check that out. Yep, that's right. Okay? So that's pretty neat. I mean, you look at this equation, and you just see from observation that 1 is a solution, and now this formula just works out perfectly to give you the second independent solution. So the most general solution to this equation, again, I will write on the board, would be what? If you're asked to write down the most general solution to that linear second order equation, the answer would be y of x equals some arbitrary constant c1 times 1, which is just c1, plus c2 times the quantity x cubed minus 3x, or c2 times this guy over here. Okay? Okay. So that's it for reduction of order. Okay? And again, you could, do it any way you want. I mean, I would suggest this because it's almost like a plug-in. Okay? Again, I don't expect you to memorize that. But realize where it comes from. Okay? The way we derived that formula, we just took the general equation and set the solution to be y1 times u, and then continued from there. Okay, we have 15 minutes. Okay, so let me just introduce the next topic that we're going to be doing, which is linear equations with constant coefficients. Okay? This is going to be probably one of the most important topics in the sense that the majority of courses that you'll be taking in heat transfer fluids and dynamics, circuits, okay? Many of these differential equations that you encounter are going to be linear equations with constant coefficients. And this is one of the areas that the story is complete, in the sense basically that there's no holes, the theory is well known, and by the time in another week or two, you'll be able to solve any linear equation with constant coefficients. Variable coefficients is a little more tricky, okay? But it's all under the same topic, right? What I'm going to do now is consider the equation L on y equals 0. We always start with the homogeneous, and then we'll go back and see how to get the inhomogeneous solution. But now, I'm going to have constants. A(n) of x will be a constant. A(n minus 1 of x will be a constant, okay? So in the general case, all the theory that we discussed, the whole stuff about superposition, and how to get the general solution of inhomogeneous equation, that all applies even with variable coefficients, where these coefficients are functions of x. But what we're going to do now is specialize to the case of constant coefficients. Okay? I think what I'll do is just, maybe, I don't want to start anything really involved. Okay? You know what? It's not really, I don't want to start even, okay, because it's one of those things I'm going to have to just redo it again. So, a little break over here. Usually that doesn't happen. Okay, so just be on the lookout for the homework, okay, which I'll probably post today.